Hello students, in this video we're going to be talking about the points of concurrency. This is the 7th lesson in Unit 5 about triangle centers, and now we're starting to talk about the actual centers of the triangles. You remember earlier on in the unit we talked about different types of lines that you could draw inside triangles. For example, we could draw angle bisectors, we could draw perpendicular bisectors, we could draw altitudes, and we could also draw medians. Once you draw enough medians or altitudes or perpendicular bisectors or angle bisectors, they eventually end up meeting in the same place, and those places have 4 different names based on the type of line that you draw inside the triangle. Let's take a look at the learning target. Our objective for today, we're going to be able to state the points of concurrency, identifying them by name, by remembering this acronym. All of my children are bringing in peanut butter cookies. Now, it sounds like a very silly acronym to say, all of my children are bringing in peanut butter cookies, but remember, it's supposed to be memorable. You're supposed to remember the words so that you can use those words to remember the different types of centers. And once you remember the acronym, all of my children are bringing in peanut butter cookies, you can say, well, A, O, M, C, A, B, I, and then P, B, C are the letters you're supposed to remember. What do these mean? Don't worry, you'll find out soon enough. All right, in the do now it says to state which diagram corresponds to the following geometric terms. We learned all of these geometric terms. They're in your notes and they're in the previous videos. So pause the video, try this one out. The do now has 1, 2, 3, 4 different triangles in it. Try this out and see which ones corresponds to which lines that we talked about before. All right, for letter A, you can see that this side of the triangle XY has these 2 markings on it, which indicates that this point here is the midpoint. So we've identified that this line that we drew inside the triangle intersects at the midpoint. And you can also see that the angle marker that's here, this right angle marker indicates that these 2 lines meet at a right angle. In other words, they are perpendicular. Now that we know that these 2 pieces of information are correct, that this is a line that is perpendicular to the opposite side and passes through the midpoint, we can correctly identify it as the perpendicular bisector. Remember, if you're ever trying to identify a line that's drawn through a triangle, you look for the characteristics of it. Looking at this triangle, we can see triangle ABC with the line through at AD. One thing that you can observe right away is that the line that's drawn inside the triangle passes through one of the vertices, that vertex here. And you can also see that this line, similar to the perpendicular bisector, meets the base at a right angle. So we know that it is perpendicular to the base. So we have to look back at our notes and look for the line that's drawn inside of a triangle that passes through a vertex and is perpendicular to the base. And it turns out that's an altitude. And the main difference between a perpendicular bisector and an altitude is that the altitude must pass through the vertex, whereas the perpendicular bisector must pass through the midpoint of the opposite side. Moving on to the next 2 lines that you can draw through a triangle, you can see that in this triangle, it doesn't say that D is the midpoint of BC, so we're not sure about that. But it does show that these 2 arcs are the same exact measure, which means that this line AD bisects angle BAC. So we put these hash marks in the 2 arcs, and we say that this line AD bisects the angle. Of course, if that line bisects the angle, we're going to call it an angle bisector. You should remember angle bisector from a previous unit. We didn't even go over it in this unit because we talked about it in units past. Last but not least, you can take a look at this one. And remember, we're only going to go off of the information that it gives us. So this angle sort of looks like a right angle, but it doesn't give us that, so we can't assume that. But what we do know is that these markings indicate that BD is congruent to DC, which means that D is a midpoint. Another piece of information I know is that AD passes through or intersects a vertex. So the name of a line that's drawn within a triangle that passes through the midpoint and the vertex is the median. Just as a quick refresher, they all have different characteristics about them. The perpendicular bisector passes through a midpoint and is perpendicular to the opposite side. The altitude passes through a vertex and is perpendicular to the opposite side, just like the perpendicular bisector. The angle bisector doesn't necessarily have anything to do with the midpoints or being perpendicular, but it does bisect the angle or bisect one of the vertices. And for letter D, for median, you can tell that it passes through a midpoint and through the midpoint, which is down here, and through the vertex. All right, now that you've identified all of these types of lines, let's talk about points of concurrency. A point of concurrency is just that, a point where 2 things concur or intersect each other. When three or more lines intersect in a single point, they are concurrent. Their point of intersection is called the point of concurrency. As a matter of fact, you can identify a point of concurrency with fewer than three lines. Once you draw two different altitudes or two different medians or two different angle bisectors, whatever point that they intersect at, that's also a point of concurrency. So we can even correctly say when two or more lines intersect at a single point, they're concurrent. All right, moving forward. All right, in this next section, I'm going to show you a couple of different centers of triangles and identify how to find them. The first one that we want to talk about is incenters. Oh wow, that's an ugly highlighting. There we go, much better. Anyway, the incenter is located at the intersection of the angle bisectors. So you can see here that the diagram has three different angle bisectors drawn. You can tell they're angle bisectors because both of these angles here are congruent, both of these are congruent, and both of these are congruent. They have the same number of hash marks. And when all of those three angle bisectors are drawn to the center of the circle, you can see they meet at one point. That point is called the incenter. One piece of information that you must know about the incenter is that the incenter is equidistant, same distance away from the three sides of the triangle. So in other words, any line that you draw from the incenter to the opposite side of the triangle, all of these lines are going to be the same distance. Equidistant means same distance. Next, we're going to be talking about the circumcenter. And the circumcenter is located at the intersection of the perpendicular bisectors of the sides. You can see here that there are three perpendicular bisectors drawn. You can tell they're perpendicular bisectors because perpendicular means they have right angles to the side. And bisector means they intersect that side at a midpoint. This is the midpoint here. This is the midpoint here. Those two hash marks indicate that this is the midpoint, and this is a midpoint of this side. The one hash mark and one hash mark indicates that. So now that we have all of these three perpendicular bisectors drawn, you can see that they meet together at this circumcenter. The things that you need to know about circumcenter are that the circumcenter is equidistant to the three vertices of the triangle. So, in other words, if I draw a line from the vertex to the circumcenter from all three vertices, all of these lines are going to be the same length. We also know that in an acute triangle being a triangle with three acute angles, the circumcenter is going to be inside the triangle. However, if we were to draw an obtuse triangle, it will fall outside the triangle. And you can see here I put in a little example. In this obtuse triangle, the circumcenter is where the perpendicular bisectors meet. These three perpendicular bisectors meet outside of the triangle. And finally, in a right triangle, the circumcenter is going to be the midpoint of the hypotenuse. In other words, it's going to lie on the hypotenuse. And you can see here, I pasted in another example of three perpendicular bisectors being drawn, and those perpendicular bisectors all intersect in that point of concurrency of the circumcenter, and you can see that it's the midpoint of this hypotenuse. All right, that's a lot of terminology for you, but it's something that you do have to remember. So if you're thinking you're not going to remember this terminology, pause that video, rewind it, and watch it again. All right, moving on to centroid. Centroid is another type of point of concurrency. And the centroid is located at the intersection of the medians. You remember medians connect a vertex to a midpoint. So this is a vertex to midpoint connection, vertex to midpoint, and they intersect here in the middle. That's the centroid. We call it a centroid, and one of the pieces of information that we know about it is that it's 2/3 of the distance from each vertex to the midpoint of the opposite side. What does that mean? In other words, if you were to take a look at the measurements of length of this piece of the median and this piece of the median, the parts that are split up by the centroid, this part would be twice as big as this part. So in a brief example, if the distance from the centroid to the opposite side was 5, the distance from the centroid to the vertex would be 10. It would be twice as big. Last but not least, let's talk about orthocenter. An orthocenter is located at the intersection of the altitudes. So hopefully you're seeing the pattern here. Each of these different types of lines are meeting at a different type of center. And this one is called the orthocenter. An orthocenter is important because in an obtuse triangle, the orthocenter is going to be outside. And in a right triangle, the orthocenter is going to be at the vertex of the right angle. But in an acute triangle like this, the orthocenter is going to lie inside. So let me give you a couple of examples of orthocenters in those other types of triangles. In this example that I've pasted in here, this is an obtuse triangle. It's got an obtuse angle here. And all of these dotted lines are altitudes. They're altitudes because they are perpendicular to the opposite side and they pass through a vertex. Anyway, when you see all of them intersect, they're outside of that triangle. That orthocenter is outside the triangle. So orthocenters can be outside the triangle, as well as circumcenters can be outside of the triangle. And last but not least, let me show you a picture of the orthocenter of a right triangle. And here's such a picture. Wow, you wouldn't believe the things that you can find on the internet. I just typed in orthocenter right triangle and it popped right up. Anyway, this is a right triangle, and all of the altitudes drawn to this right triangle intersect at one point. That orthocenter is the vertex of the right angle. So in right triangles, some of the centers are in specific places. The orthocenter is going to be on the vertex of the right angle, and with circumcenters, that circumcenter for a right triangle is going to be the midpoint of the hypotenuse. Anyway, you might be thinking to yourself, first of all, why are they telling me all this? Well, the reason we're telling you this is because you need to be able to spit out these pieces of information. Just like in a science class, you need to memorize the parts of a cell, and just like in a history class, when you have to memorize all sorts of historical dates of people taking over countries, in geometry, you got to memorize definitions of centers of triangles and what they correspond to. Orthocenters correspond to altitudes, centroids correspond to, medians, incenters corresponds to angle bisectors, and circumcenters correspond to perpendicular bisectors. Okay? Now, here's the despair part. Here's where you think to yourself, oh man, I'm never going to remember these. But that's okay, because remember back at the beginning of the lesson, we gave you this nonsense sentence, all of my children are bringing in peanut butter cookies. It turns out that that just wasn't a sentiment. That is, hopefully my students are going to be bringing me peanut butter cookies. That is a statement that will help you remember all of these 8 things that you have to remember. So, moving on to the last part of the notes here. All of my children are bringing in peanut butter cookies. Here's what they mean. All of, altitude, corresponds to orthocenter. How about that? My children, median, centroid. Are bringing in, angle bisector incenter, ABI, right? Peanut butter cookies, PBC, stands for perpendicular bisectors, circumcenters. The one tricky part about this, I would say there's probably only one tricky part, is that some of these things have the same letters, right? For example, altitude has the same letter as angle. So the way that I remember that angle bisector corresponds to incenter and altitude corresponds to orthocenter, I say all of my children, that's 2, and that's 2, and then are bringing in, there's 3 words here, peanut butter cookies, there's 3 words here. So I remember there's 2 words, and then 3 words, 3 words. Hopefully that makes sense to you. And then the last thing that is sometimes confusing or hard to remember is that centroid and circumcenter both start with the letter C. And there's 2 ways to go about this. You could just remember that this C stands for centroid, or you could think to yourself, this is a little bit deeper, but you could think to yourself, the last word is cookies. Cookies are circles. Circumcenter, circles. Why not? All right. Let's move on to the circle relationships. Now, later on in the curriculum, we're going to be talking about 2 different terms. The terms are for when things are drawn inside or things are drawn outside of a shape. For example, in this case, you can see that this circle is drawn around the triangle. The word for drawn around is circumscribed, from the Latin for circle, circum, or around, and the Latin for drawn, which is scribed. So circumscribed means drawn around. This circle is drawn around the triangle, whereas this circle is drawn inside the triangle. It is inscribed in the triangle. So we say that circle is inscribed. It is an inscribed circle. Similarly, we say this is a circumscribed circle. So a circumscribed circle has a circumcenter, a center that is where all the perpendicular bisectors intersect. And this circle, this inscribed circle, has an incenter where all the angled bisectors intersect. Just another set of words that you have to remember for later. All right, let's take a look at a model problem. It tells us that P is the centroid of triangle QRS, PT is 8, and ST is 24. You need to find these 3 things, and in order to do that, you need to remember the concepts that we talked about before. Since it's a centroid, there's a relationship that corresponds to that. So pause the video, try this out, and then see if you got it right. All right, you should remember that a centroid splits the median into 2x and x. In other words, this point P splits every one of these medians into 2x, which is the part that's touching the vertex, and x, which is the part that's touching the opposite side. The other information that they give us in this problem is that PT is 8 and ST is 24. So now let's start thinking about what information we know. We know that this measurement is 8. We also know that P, the centroid, splits this median RT into a ratio of 2 to 1. In other words, this part is 2x and this part is x, as labeled here. So if I know that this part is 8, this part is going to be twice as big. So I can label this from here to here, from R to P, that's 16. It's just twice as big as this part. Great. Now let's see, are we supposed to find RP? Looks like we are. So we know that PR, or RP, is equal to 16. What units? We're not told, so we can just say units. The next thing that we know is that this line, RT, is a median. A median intersects two things. It intersects a vertex and a midpoint. So I know that RT intersects a vertex here, and it also intersects T, which is a midpoint, which means that TS is 24, so TQ must also be 24. Are we asked for TQ here? Doesn't look like it, but we are asked for QS, and we can figure out QS very easily by using combining terms, or really the segment addition postulate, where this segment plus this segment is equal to the longer segment. So this is 48 units. And last but not least, we're asked to find RT. Well, we have all the information we need to find RT. All we need to do is put it together. Another example of segment addition, let's do 16 plus 8. That should just give us 24. Now this might seem trivial. It might have seemed pretty easy, and it was pretty straightforward. But in order to answer all of these questions, we needed to know that centroid is where all the medians intersect, and also that centroid splits the median into 2x and x. So we needed to know what centroid was in order to unlock all of these procedures. All right, I would ask you to go on to the check for understanding, but of course you know you're going to be doing that in class, which means we've reached the end of this video. All right, this was the video on points of concurrency. Good luck studying.